Hey guys, Mr. Betts here. I want to talk to you about something called the mean value theorem. It's a theorem that we'll be able to use to gain some insights about functions under certain conditions. So let's jump into it and talk about what it tells us. So in a general sense, if we look at a function, we've talked about average rate of change quite a bit, and we've talked about instantaneous rate of change quite a bit. And we've talked about average rate of change as being the slope of a secant line. So in this example, it would be the slope of the line through the 2 points at the ends. And what the mean value theorem does is it gives us a relationship between the slope of the secant line through the two endpoints of some interval and the slopes at different points on the interval. So in this case, you may notice that there are a couple of points on this interval where the slope of the tangent line and the slope of the secant line are the same. It actually turns out that under certain circumstances, this has to be the case. So remember, in an application, the average rate of change over an entire interval and the instantaneous rate of change have a particular meaning. If you think about it in terms of, say, a moving vehicle, the average speed of a moving vehicle is the total distance the vehicle traveled divided by the total time that it took to travel it. That would be represented in a picture like this as the slope of the secant line. The instantaneous rate of change, on the other hand, would be the slope of the tangent lines. What's happening at these particular points right here is that the speed of the car, or the velocity of the car at those points, matches up with the average rate of change, or the average speed. So the mean value theorem says that that has to be the case. All right, but it has to be the case under certain conditions. The two conditions are that the function has to be a continuous function, and it has to be a continuous function over the closed interval. So including the endpoints, the continuity has to hold, and it has to be differentiable on the open interval. So the differentiability does not have to hold at the endpoints. That means that we could have, for example, a vertical tangent at one of the endpoints. One of the endpoints could be a corner or a cusp as we go to the outer part of the interval, but between A and B, it does have to be differentiable. And if those two conditions are met, then there must exist, I'm going to talk about this word exist in a little bit, but there must exist a point, at least one point, I should say, within that open interval where the instantaneous rate of change, so instantaneous rate of change is a derivative, is equal to the average rate of change, and that's the slope of a secant line. So if you look at this equation right here, this is basically saying here's the mean value theorem in equation form. The left side of the equation is the instantaneous rate of change at some point C. Notice that we're saying C is some point in the open interval between A and B, and that has to equal the average rate of change. Now, I'm going to talk a little bit more about what this word exists means. I think you know what it means, but in the context of this theorem. But I just want to look at some examples. So the first example here is just like the one that I showed you at the beginning, and we can see that we have the line that is representing the average rate of change, and we can see that there are a couple of points on this interval where the instantaneous rate of change, or the slope of the tangent line, is going to be equal. If we look at some other functions where this might fall apart, this function right here, this graph, does not follow that. And the reason it does not follow that, and it doesn't have to, is that we have this corner here. So there is no point on this interval where the slope of the tangent line is equal to the slope of the secant line. In particular, the slope of the secant line here looks like it's about 1/4, and the function itself has a slope of 0 on one interval, and it has a slope of 1 on another interval, and it's never actually equal to 1/4. Well, the mean value theorem doesn't say anything about this function because this is not a differentiable function. So since it's not differentiable here at the point 6, then the mean value theorem doesn't really tell us any information. If we look at another example here, we have a discontinuous function. So since the function is not continuous on the interval, we have this jump discontinuity at x equals 1, then the mean value theorem doesn't apply. So we have a slope here of 1/4, and at no point on this interval is the slope of the tangent line equal to 1/4. So mean value theorem doesn't really tell us anything here. In this example, I want to point out that the mean value theorem does not apply because we do have this jump discontinuity here at 3. However, if we look at the average rate of change, the slope of that secant line, it does look like we're going to have a tangent line up here that has the same slope. So just because the mean value theorem doesn't apply doesn't mean that we can't have points where the instantaneous rate of change or the slope of the tangent line is equal to the average rate of change. So I mentioned this earlier. I want to talk about what the word exist in this theorem means. The mean value theorem is what's called an existence theorem. So what that means is it tells us that under certain circumstances, we know something has to exist. In this case, we know that there is some point on the interval. So there is at least one point on the open interval from A to B where that equation for the mean value theorem is. What the mean value theorem doesn't do is it doesn't tell us where it is. So it says somewhere on the interval, we're going to have this point where it meets these certain conditions, but it doesn't say where. Now, that being said, we can use this equation right here from the mean value theorem that has the instantaneous rate of change equal to the average rate of change, and we can use that equation to actually find the values of C. Okay, so when we apply the mean value theorem, it just says, yes, something has to exist. Okay, when certain conditions are met, specifically if the function is continuous on the closed interval and differentiable on the open interval. However, we can find the points on the interval depending on the function. As long as we can take the derivative of the function, then essentially what we can do is figure out what the slope of the secant line is, that's the average rate of change, figure out what the derivative is, plug in C into the derivative, and then set them equal and solve. So we're solving for C. Remember, the mean value theorem says that there has to be at least one value of C. It's possible when you solve an equation like this that there's more than one. So you could have 2, 3, you could have, I shouldn't say infinitely many because we're going to be on a finite interval, but we could have lots of different values of C.